Hi there, Mr. Sutton here with the BC Calculus 711 Extra Practice Solutions on Direct Comparison Test. For this problem, we want to know if this series converges absolutely, conditionally, or not at all. First thing to do is to recognize that cosine of pi is really -1. So this is an alternating series, -1 to the n over n factorial plus 1. It's probably going to converge at least conditionally, but let's see if it converges absolutely by considering this without this -1 to the n. So I'm just going to consider the series of 1 over n factorial plus 1. And I'll go from there. So this one I'm very sure is going to converge. N factorial is a very fast growing function. So let me compare it to something that I know is also going to converge, like 1 over n squared. Now this series is a p-series with a p-value of 2. Since that's greater than 1, I can easily show by the p-series test that this converges. Now comparing that back to my original series, this original series is clearly growing faster in the denominator than my comparison series. So I can say 0 less than or equal to 1 over n factorial plus 1, less than or equal to 1 over n squared. And I know this is going to be true at the very least when I get to n equals 4. At 4, we've got, this is 24 plus 1, so 25 down here versus 16. Bigger denominator, smaller fraction. So this is true for n greater than or equal to 4 at the very least. And now since I've shown that I have a series that is smaller than another series that converges, my original series must converge, and it's going to converge in this problem absolutely by the direct comparison test. For this problem, we want to figure out whether this series converges or diverges. So this doesn't really have an easy test. I mean, it's not geometric. It passes the nth term test. Ratio test isn't going to help us out a whole lot on this one. This ln term is going to be kind of weird to try to mess with. So I'm going to try using a comparison test with another series that I know converges or diverges. Now probably the closest series to this one is n over n cubed. And this is a nice series to compare it to because this series is actually smaller than this comparison series. Now this comparison series, you could reduce this to 1 over n squared, which is a p-series with p equals 2. Since that's greater than 1, we easily show by the p-series test that our comparison series converges. And I'm pretty sure that my original series is going to converge. I just have to show that this is less than this. And in fact, it is. The only difference between my original series and my comparison series, when you get down to it, is ln versus n. Since that's in the numerator, we can say that 0 is less than or equal to ln over n cubed, which is less than or equal to n over n cubed, or 1 over n squared, either of those. And this is going to be true pretty much immediately, but let me say n greater than or equal to, well, I guess we could go with 1. I mean, let's just test it out to be sure. So if I plug in 1, this is going to be 0 over 1, which is 0, and that's definitely going to be less than 1. If I plug in 2, well, I've got something smaller than ln, or smaller than e rather, being ln. That's going to be less than 1 up here, and the denominators are going to be exactly the same all the way through. So this is definitely true, n greater than or equal to 1. But if you're not sure, you could always make this like 100 or something that you know is going to be safe. Anyway, since I've got a series that's less than 1 I've already shown converged, my original series then converges by the direct comparison test. For this problem, we're told that the series with a diverges and 0 less than or equal to a less than or equal to b. So this is talking about the direct comparison test when you have these three things, 0 and the 2 series being compared. By the direct comparison test, if I have a diverging series, like a, that means that, and that's less than some other series, like b, and they're both positive, that means that b must also diverge because it's bigger than a series that already diverges. So from this we can conclude that b diverges. So that's going to be answer choice E. It says that explicitly. Now just taking a quick look at these other answer choices, A through C are no good because we have this -1 to the n thrown in, this alternating. So whatever else you want to conclude about the original, we really can't conclude anything about the alternating version of a series just based off of what the original is doing. And now choice D is directly the opposite of what we need to conclude. So yeah, choice E. For this one, we're trying to prove if 1 over n to the n converges or diverges. Now, there aren't a whole lot of good tests to deal with something like n to the n, so I'm just going to use comparison to a series that's easier to prove convergence for, such as 1 over 2 to the n. Now, this series is a geometric series. We have an absolute common ratio of 1/2, which, since that's less than 1, easily is provable to be converging. So now, comparing it to the original series, 1 over n to the n is smaller than 1 over 2 to the n. N to the n is growing faster, so I'll write 0 less than or equal to 1 over n to the n, less than or equal to 1 over 2 to the n. And now, which n values is this true at? I mean, you can pick as large of an n as you want, but if we go with 3 for n, we've got 1 over 3 to the 3, so that's 1 over 27, versus 1 over 2 to the 3, 1 over 8. So definitely 3 works. We'll go with 3. And now, since I've shown that I have a series that is smaller than a series that converges, I've shown that 1 over n to the n converges by the direct comparison test. For this problem, we're trying to figure out if this series converges absolutely, conditionally, or not at all. We'll start by considering the absolute case, so I'll just stick all this in absolute value. Although, if we're being honest, the only thing that has a chance of being negative is this sine of x function. And this is kind of weird, too, because they're not telling us what x is. X could literally be any real number, so we have to consider all those cases when we do this problem. All right, so there aren't a lot of good tests to use on this. It's not geometric. The ratio test is going to be kind of a mess with this x term in there. And there's not a p-series. What else is there? I mean, integral test is going to be a nightmare on this. So we're going to try a comparison test. I'm going to pick something that's close enough to this that I can compare it, that's easy to find convergence for. So let me see here. Sine of x can't really be more than 1 or less than negative 1. So for my numerator in my comparison series, I'm just going to use 2, because that compares pretty well to 2 times something that alternates between negative and positive 1. For the denominator, I'm going to pick something. I don't want really n factorial, because then I have to use ratio test to figure out if that converges. So I'm just going to use n squared. I have a pretty good suspicion that this series is going to converge, because factorial is a pretty fast-growing function for the denominator. So I'm going to pick something I know also converges. I'm going to pick 2 over n squared. Now, for this one, proving convergence, you can actually just take a 2 out here, and now inside you have a p-series with a p-value of 2. Since that's greater than 1, we know that this is going to converge by the p-series test. So now comparing this back to my original function, since sine can't be bigger than 1, that means that, at least in the numerator, we're smaller than or equal to this comparison series' numerator. In the denominator, since this is n factorial is going to give us a larger number than n squared for really almost any n value. Actually, let's test out a few of them. At n equals 1, we've got 4 versus 1, so that's bigger. At 2, we've got, let's see here, 5 versus 4, still bigger. At 3, we've got 9 versus 9, so that's a little closer. But then at 4, we've got, this is going to be 27 down here versus 16. So yeah, for n greater than or equal to, let's just say 2 to be on the safe side, we know that these are both positive, and this expression is less than this other expression. So since we've shown that we have a series that's smaller than another series that converges, we can say this whole thing converges absolutely by the direct comparison test. On this problem, I want the interval of convergence for this series. Since this is not a geometric series, we use the ratio test to get our interval of convergence. So I have the limit as n approaches infinity of absolute value of, and then we have a big fraction with the n plus 1th term over the nth term for this thing. So n plus 1th term, we have x to the n plus 1, n plus 1, and n plus 2. And now the nth term is just going to be what I have in my series here. Same change flip to get my fraction simplified. Numerator, I've got x to the n plus 1 and n plus 1. In the denominator, I've got n plus 1, n plus 2, and x to the n. For this next step, I'm going to make this look a little bit prettier. These n plus 1s actually can cancel out. That almost never happens, but we'll take it. and then x to the n plus 1 and x to the n. Those cancel out, leaving me with just x upstairs because I'm subtracting the exponents, subtracting those n's. So I have an x and I have an n in my numerator. Denominator, the x is gone, the n plus 1 is gone, we just have n plus 2. And now as n approaches infinity, I can forget about this little plus 2 down here. So it's really just n over n, which reduces to 1, and we still have this x left over upstairs. So absolute value of x, and that's going to be less than 1 if I'm trying to get interval of convergence. So my interval of convergence then, writing this without absolute value, is initially, this is my first draft, my rough draft, I'm going to have negative 1 less than x less than 1. But I'll put a question mark because I'm not really sure about those endpoints. Let's go ahead and test those out. At x equals negative 1, if I plug negative 1 in for x, I've got negative 1 to the n over all this stuff. Now, this is a series that alternates, obviously, and it's decreasing in absolute value to 0 because we have this growing denominator. Since that's the case, we know that this is going to converge by the alternating series test. So now we move on to the other endpoint, positive 1. If x is positive 1, this is going to be 1 over all this stuff. So this is, I multiplied this out actually to get n squared plus n. Now this is almost a p-series, so we're going to compare it to a p-series. I'm going to compare this to 1 over n squared, which I know is a p-series with a p-value of 2, which, since that's greater than 1, this series here is going to converge. Comparing these two series now, since these are exactly the same except we have a plus n down here, larger denominator means smaller overall fraction, so I can say 0 less than or equal to 1 over n squared plus n, which is less than or equal to 1 over n squared. Since I've shown that my series is smaller than another series that we proved converges, this original series here must also converge by the direct comparison test, and this will converge for n greater than or equal to 1. This is immediately true starting at 1. So converging by direct comparison, which means when I go back and do my interval of convergence, I've got negative 1 less than or equal to x because that first one converged by alternating series, and then I can write less than or equal to again 1 because we converged again by direct comparison. For this one, we're trying to find the interval of convergence for this series. Since this is not geometric, let's use the ratio test on this. So I have the limit as n approaches infinity of the absolute value of the n plus 1th term over the nth term, so the nth ratio essentially. So I've got a big fraction. Upstairs I have 10x all raised to the n plus 1 over ln of n plus 1. Denominator is just going to have exactly what we see in the series here, the nth term. Same change flip to simplify this fraction now. Numerator, I've got 10x to the n plus 1 times ln of n. Denominator, I've got everything else, ln of n plus 1 and 10x quantity to the n. I can simplify these 10x's to the n powers here by subtracting the exponents. That leaves me with a 10x to the first power upstairs to go with my ln of n. Downstairs, all I have left is ln of n plus 1. Now, as n approaches infinity, this little plus 1 inside the ln goes away. ln of n divided by ln of n is just going to cancel, so you just end up with a 10x inside the absolute value. And now I'll set this less than 1 to get the interval of convergence. I can actually divide everything by 10, so I have absolute value of x less than 1/10. And now to write this without the absolute value, my interval of convergence, rough draft anyway, is going to be negative 1/10 less than x less than 1/10. All right, now I have to go and test those endpoints because I'm not really sure, since I used ratio test, if we converge at the endpoints. So testing out x equals negative 1/10, let's see what that does to my series. Well, negative 1/10 times 10 here is just going to be negative 1. So we have negative 1 to the n over ln of n. This is an alternating series, and since my denominator is growing, this is decreasing in absolute value to 0, which means that this series is going to converge by the alternating series test. All right, so this first endpoint converges. How about this other one? If we plug in 1/10 for x, let's see what happens to our series. 10 times 1/10 is just 1. So I have 1 to the n, which is just 1, all over ln of n. I'm pretty sure this is going to diverge, but to prove it quickly, I'm going to use a comparison test. So I'm going to compare this to the harmonic series. That's the closest one I can think of that's easy to prove convergence that's going to diverge. So compare this to 1 over n, starting at n equals 2, just to make it consistent here. This is the harmonic series, which we know diverges, so really easy to prove that. And now, in the order that these things go in, since ln of n is a smaller denominator than n, that means it's a bigger overall fraction. So when we're writing the order of things, we can say 0 is less than or equal to 1 over n, which itself is going to be less than or equal to 1 over ln of n. 1 over n is going to give us a smaller overall result than 1 over ln of n. And this is going to be true for values of, we'll just say 2 or greater to be on the safe side, because we don't want to have ln of 1. That would just be 0. But starting at 2, we're good. So this means that since I've proven I have a diverging series that's less than the original series, that means the original series must also diverge by the direct comparison test. Going back and writing my intervals of convergence now, the final answer, we've got negative 1/10 less than or equal to x, because we converged at that spot. And then we're just going to write less than 1/10. For this problem, we're given that this A series converges, and we're told that the terms of the series are always positive. So we want to know what has to be true based off of that. First thing, limit of the n plus 1th term over the nth term is 0. Well, this is kind of like the ratio test, but the ratio test says that this ratio has to be less than 1, or it's ambiguous if it equals 1. So let's just say that limit has to be less than or equal to 1. Inconclusive, but still possible at 1. So in any case, it doesn't have to be 0. It could be 1/2, and that would still be just fine and consistent with this. So we can eliminate A. 0 is not necessary for that limit. All right, B. They're saying the absolute value of all the terms has to be less than 1. Well, the terms have to all be positive, so that much is true. But does the value always have to be less than 1? I can think of a counterexample here. Let me take the series 1 over n squared, which I know converges, and let me just put a 2 in the numerator, like so. So I'm allowed to factor this 2 out of the series like this. And then I can write this series as, let's see, this would be 2 over 1 squared, so 2, and then 2 over 4, and then 2 over 9. So this definitely converges. It's a p-series with a p-value of 2, which is larger than 1. However, the absolute value of all the terms, the individual terms, is not less than 1 across the board. So B can be eliminated with this counterexample. All right, next one, they're saying that the series sums to 0. Totally doesn't have to be true. It has to have an nth term whose limit at infinity is 0. However, the series itself could be any finite number and still count as converging. Next one, n times a sub n diverges. Well, there are times this can happen. If your a sub n was 1 over n squared, multiplying n by that would give you the harmonic. But what if your series was n times 1 over n cubed? Because 1 over n cubed also converges. Well, n over this would give us 1 over n squared, which we know converges. So D can also be eliminated with a cleverly picked counterexample. Now for E, we're taking a series that converges and dividing it by n. So this is actually going to make it converge even more if that's possible, because we can say that 0 is less than this new series, which is less than the a sub n series that we know converged. If we have a series that we know is less than another converging series, that series itself must converge by the direct comparison test. So E is guaranteed, and that's the one we're going to pick. For this no calculator free response, we're given the function 1 over x squared plus 9, and for the first task, we want to evaluate the improper integral 3 to infinity of this function, and then or show that it diverges. All right, so we need to rewrite this with a limit. I'm going to write this as limit as b approaches infinity of integral from 3 to b of all that stuff, so dx over x squared plus 9. And I can't quite take the antiderivative just yet. It's pretty close to 1 over x squared plus 1, which would be arctan if I was taking that antiderivative. To get it in a form that arctan can deal with, I need to get it so that I have something squared plus 1 in the denominator. So to do that, I'm going to get kind of fancy and factor a 9 out of my denominator. That'll leave me with a 1/9 x squared plus 1 inside. And then I can express this 1/9 x squared as 1/3 x quantity squared. And this is now something that I can take arctan of. So I'm going to have a 1/9 out here. When I take the antiderivative and get arctan out of this, I'm going to divide by that tail of 1/3. So I'm actually multiplying by 3. 3 over 9 is going to give me 1/3 eventually. So just when the dust settles, I end up with 3 over 9. I still have the limit as b approaches infinity. 3 over 9. And then inside, I've got arctan of 1/3 x evaluated from 3 to b. All right, so I can rewrite this as just 1/3 out here. And inside now, I've got arctan of b over 3, or 1/3 b, minus arctan of 1. Evaluating this is a little bit tricky. We still have the 1/3 out in front. We'll start with that. And now, as b approaches infinity, so this is as I approach infinity inside arctan, what is happening to the output? Well, arctan gives me back the angle when I plug in, it gives me back the angle when I plug in the slope. You give me the slope, I give you back the angle. So as the slope becomes infinite, what angle am I approaching? Well, arctan only operates between -90 and +90. So I'm approaching the angle 90, or pi over 2, as my slope gets perfectly vertical. So this is pi over 2 for arctan of 1/3 times infinity. And then for this other piece, arctan of 1, that's just going to be pi over 4, 45 degrees. And so now you could simplify this or leave it the way it is. If you do simplify this, this is really 2 pi over 4 minus pi over 4 inside, which is just pi over 4. 1/3 of that gives us pi over 12. For this problem part, we want to determine whether the series from 3 to infinity of f of n converges or diverges. State the conditions of the test used to determine convergence or divergence. All right, so there's a couple ways to do this. One way is to use what we did in part A. Remember that we found an integral from 3 to infinity of this same function. So that means we could use the integral test. But before we can do that, we need to state that this function is a few things. First, for one thing, it needs to be for n greater than or equal to 3, which is where we're starting here. The function needs to be continuous, which it is. I mean, there's no holes in here at all, actually. It's impossible to be doing 1 over 0 if you're squaring and then adding something. It's also going to be, let's see here, positive. It has to be positive to meet the integral test. And it is positive. Again, you can't get negative numbers anywhere out of this. And since our function is increasing in the denominator and not doing anything in the numerator, overall this is a decreasing function. So once we've established that this function is continuous, positive, and decreasing, we actually just have to state it because it said state the conditions. We can go ahead and use the integral test. Well, the integral test basically says take the integral of this thing, and the behavior of the integral is going to match the behavior of the series. From part A, we saw that our integral converged. It came out to something like pi over 12, but the important thing is it came out to a finite number. It didn't diverge to infinity. So that means by the integral test then, the series here also converges. At this point, we're going to do part B again using a different method. So if you did not use integral test for this thing, you actually could have used a comparison test. I'm going to use direct comparison on this one. So I noticed that 1 over essentially n squared plus 9 is pretty close to the p-series 1 over n squared. So let me compare it to that p-series. This is a p-series with a p-value of 2. Since that's greater than 1, this comparison series converges. All right, so now we see here that 1 over n squared plus 9, since it has a larger denominator than 1 over n squared, it's actually a smaller number. So we can say 0 less than or equal to 1 over n squared plus 9, less than or equal to 1 over n squared. And this is definitely going to be true for really all n values, but we'll just start it at greater than or equal to 3 to be on the safe side. Doesn't really matter how far out you start it as long as it's true. So now because I've shown that my original series is smaller than a series that we know converges, the original must also converge by the direct comparison test. On this problem part, we're trying to figure out whether this crazy-looking series converges absolutely, conditionally, or diverges. So on these problems, we always start by testing for absolute convergence, which basically means we're going to lose this -1 to the n that makes us flip back and forth between negative and positive. So I'm just testing n squared plus 9 over e to the n for convergence. And to do that, I'm going to use the ratio test. I'm using the ratio test because I've got a combination of polynomials and exponentials, so that's usually a good test in this situation. And I would use a comparison test with 1 over e to the n, but this is actually greater than 1 over e to the n, which converges, so that would not go the right way with my inequality. All right, so ratio test. We have the n plus 1th term. That's n plus 1 squared plus 9 over e to the n plus 1 for the n plus 1th term, over the nth term, so n squared plus 9 over e to the n. Let me do a little same change flip now to get my fraction a little simpler looking. So in the numerator, I still have n plus 1 squared plus 9, all of that times e to the n. I'm not going to worry about expanding this n plus 1 squared because n is approaching infinity, so this plus 1 is eventually going to go away. All right, now, so we have, in the denominator, we have e to the n plus 1 and n squared plus 9. I can cancel out some of these e's by subtracting the exponents. So that leaves me with an e downstairs to go with the n squared plus 9. Upstairs, I just have n plus 1 squared plus 9. So downstairs now we have an e times n squared plus 9. Now, as n approaches infinity, I'm going to be able to ignore this plus 1. So I'm going to have n squared plus 9, and then I'm going to be able to ignore the plus 9. So really, I just have n squared up here. Down here, I have an e and an n squared. So that just gives me 1 over e when the dust settles. And 1 over e, well, I'm using the ratio test, so I have to figure out, is this bigger or smaller than 1? E is about 2 point something, so this number overall is going to be less than 1, which means that this is going to converge by the ratio test. Since this is the absolute value version of this crazy series here, that means we converge absolutely by the ratio test.